All right, welcome everybody. Thank you for joining us today. I'll say a few introductory words and then we will move into our expert presentation and discussion. So to give a little context about the task at hand, this is a consensus study committee work of the National Academies of Sciences, Engineering, and Medicine. And our charge is to assess potential causes, consequences, and remediation of plug failures. You can find the full statement of task for this committee and the report in the link that I'll provide in the chat shortly. And to give a little more detail about the format of today's meeting, we will be hearing from Dr. Bernhard Mayer, who is the professor and head of the Department of Geoscience at the University of Calgary. And he'll be talking to us largely about this topic area in the context of monitoring hydrocarbon wells and well sites and different leakages and potential movement of subsurface fluids and gases. In addition, just logistically, I want to note that this is an open on-the-record session, and we may address any questions provided in the chat by any public attendees that we have with us today, but the priority of the meeting is for committee members to ask questions to our invited expert. To that point, I also just want to briefly remind everyone that this is an information gathering session. And what that means is the committee is in process of assembling materials to examine and discuss in order to formulate its findings, conclusions, and recommendations that will ultimately be published in our final report. Therefore, just to be mindful that the committee has made no particular conclusions at this point. And lastly, we just ask that all attendees be respectful of each other throughout this meeting. And with that said, I will turn it over to you, Dr. Mayer, for your brief presentation. Oh, and let me make sure that you can have screen sharing capabilities. Okay.
Yeah, turns out I do have not.
Okay, can you give it a try one more time?
Now it looks better.
All right, great.
Let's see how this works out. Can you see a PowerPoint slide?
No, you may have shared the wrong screen. Right now we're seeing your Zoom.
Okay. Try it a second time.
All right, there we go.
Is it any better?
Yes. Oh.
Oops.
Take your time. All right, there's your...
Any luck now?
Yeah.
And you have a full screen now?
Yes.
Okay. Yeah, as mentioned, my name is Bernhard Mayer. I'm with the University of Calgary since 1997. And so for more than 25 years, I'm now involved in geochemical techniques to monitor for movement of subsurface gases and fluids in the near surface environment. The one correction from the introduction I want to make is that I'm no longer the head of the department, thankfully. In terms of key ingredients for monitoring of migrating gases and fluids, there's a diagram of a fracked well here on the right-hand side. The three areas of interest we are involved in studying is widespread sampling and analysis of dissolved and free gases from aquifers and from soils to establish baseline conditions in the near surface environment. We are very interested in collecting information on chemical and isotopic composition of gases from the intermediate zone. So that would be below the shallow groundwater, but above the resource play. And finally, we also, as a third ingredient, need to know the chemical and isotopic composition of gases and fluids from the production zone in the various areas. And all my expertise is from resource plays in Western Canada. I have no expertise in the United States on similar issues. The types of samples and the sampling approaches we like to pursue from the left to the right on this diagram is to sample produced gases and fluids. That is typically done in produced gases in stainless steel containers. We're interested in collecting mud gas samples during the drilling of wells, so the natural gases which come with the mud to the surface. We have quite a bit of experience in analyzing groundwater samples, including free and dissolved gases. We have some experience with soil gases, either with chambers at the soil-atmosphere interface or with drive point probes where we can collect soil gases in various steps, and then relatively limited experience with surface casing vents. The analytical tools we use in our laboratory is the chemical characterization of water samples and gas samples. That includes major and minor ions in water samples, the hydrocarbons in dissolved and free gases, CO2, argon, other gases, to characterize the gas composition. And in addition to that, we specialized in doing stable isotope analysis on various compounds that includes water, dissolved inorganic carbon, sulfate, various others, but most importantly for this context, the isotopic composition of methane, and where abundant, also ethane, propane, and CO2. On the right-hand side, you see a diagram of the carbon isotope ratios of methane versus the hydrogen isotope ratios of methane. And as you probably heard before, this isotopic characterization enables to determine whether the methane which occurs is of microbial origin, a thermogenic gas, or whether it is from some other sources. I also decided to give you 3 or 4 key findings from our research over the last 20 years, which might be relevant to your panel. And all of that, again, is focused on Western Canada. On the right-hand side, you see a diagram of carbon isotope ratios of methane versus the gas dryness, concentration of methane over concentration of high alkanes. And it turns out that in Western Canada, gases in shallow aquifers at baseline, gases in coalbed methane plays, and gases in shale gas reservoirs have very different isotopic compositions. The figure on the right shows you, not sure if you can see my cursor, that would be the average composition of methane in shallow groundwater. The green dots down here are the CBM plays in several 100-meter depths. And the black dots over here, these are shale gas reservoirs in 2 to 3.5 kilometer depths in Western Canada. So the different chemical compositions indicate that measuring the carbon isotopes of methane and the dryness of the gas is a promising tool for tracing migration from gases from hydrocarbon reservoirs towards the near-surface environment. I also mentioned that we are interested in characterizing carbon isotope profiles of methane and, if abundant, ethane and propane in the intermediate zones. So as wells are drilled, it's possible to release gases from the mud shaker. And these measurements can, in fact, be done in the field, for methane at least. And when doing so, that gives us a profile of carbon isotope ratios of methane, which you see on the left-hand side from a literature source, ethane and propane, which in Western Canada do increase with increasing depths relatively consistently. So that gives us a library of isotopic composition versus various depths, which comes in handy if later on we collect gases at the near surface and try to decide from which depths they are released. Second last slide here shows you that in Western Canada, methane in shallow groundwater at baseline conditions, I should say, is almost always of microbial origin. Our research group has somewhat limited experience with analyzing gases from surface casing vents, a little bit of experience with measuring soil gases. And whenever we do that in our research areas, we often identified that these gases are most often from the intermediate zone, especially from coal zones, which are in the intermediate zone, releasing gases which then come back to the surface. My last introductory slide here summarizes a couple issues about shallow groundwater. Shallow groundwater influx of dissolved gases and formation water, in my view, is relatively easy to monitor for because we have a number of different analytical techniques to do so. And it's easy to do so if there are sufficient monitoring access points in groundwater flow direction. However, the movement of free gases in the shallow groundwater and in the water unsaturated zone, in our experience, is much more difficult to predict and monitor. That knowledge comes from a series of gas injection experiments. On the diagram, you see one of those where hydrocarbon gases were injected at depths into the aquifer. The groundwater flow direction here is to the right-hand side. So if methane were dissolved in groundwater, it would travel to the right of this diagram. However, if you have a free gas phase, buoyancy comes into play and the sediment characteristics come into play. And you see the orange is the gas distribution, the free gas distribution, that through buoyancy and tilted sediment faces, that gas goes all over the place, often in directions which are hard to predict. And in this case, they are against the groundwater flow direction, so much more difficult to assess where to find the gas outside of the wellbore. That's all I have to present up front, so happy to answer any questions on that or any other related matter.
All right, thank you so much, Dr. Mayer. I want to take a moment just to see if there are any immediate questions from our committee members. We have a few more people who've joined in. Okay, if not, Mary Kang, can I turn it over to you to provide a little more context about chapter 5 and kind of what we're looking for in a from a geochemistry lens in that chapter?
Yeah, happy to do that. Thank you. And thank you for that presentation. That was really helpful, and we're really excited to have you here in this session. It's chapter 5 is called is the monitoring chapter of this report, and it's broken down into 3 sections. The first one is environmental monitoring. And then we have well integrity monitoring. And then the third section is geochemistry. We actually took out geochemistry because there's a lot of overlaps within environmental monitoring and well integrity monitoring. Of course, there's opportunities to kind of put it back into those as subsections. But hopefully this conversation can help us here. So environmental monitoring would be more along like groundwater monitoring. Everything you mentioned about groundwater monitoring would be relevant there. And then well integrity monitoring, that could be the surface casing vent flows, but also like soil gas sampling. All of that would be very relevant. So yeah, that's kind of the high level discussion, high level overview of the chapter. I don't know if anybody wanted to add anything else. I don't know, Missy, if you were trying to say something.
Sorry, I was just saying, yes, yeah, that's fine. Yeah, let's keep going.
Okay, so I don't know if Noelle, if we should open it up to the discussion component here.
Yeah, absolutely.
Okay, Noelle, you're moderating the questions, right?
Correct. Yeah. And as you were talking, I was thinking, Dr. Mayer, one of the other sections of our report that I think might help inform chapter 5 is emerging technologies and methods. So I'm curious if in your research and your many years of experience, could you tell us any could you highlight some evolution in the methods for monitoring like methane leakages or how methane kind of interacts around in the subsurface around these well sites and how has the research changed? How have like the tools changed? If you can talk about that, I think that might help us find some direction both in our monitoring chapter as well as the what will be the final chapter of our report, which is kind of more forward looking and yeah, just looking toward the future and what needs to be further developed.
Yeah, there has been some analytical development in the last 20 years of a measurement of gas concentrations and isotope ratios has been done for more than 50 years. There are some newer technologies on the market now, which are laser-based measurements of methane concentrations and methane carbon isotope ratios, with ethane slowly coming online. These technologies enable measurements in the field on a almost immediate basis for soil gas measurements, for samples from mud gases, for instance. I've shown a picture where we have done this by taking that type of analyzer to a drilling rig and sitting there for a week, 24 hours, 7 days, collecting measurements and do the analysis right in the field. So there are some advances. The ability to measure methane, ethane, propane isotopic composition on mud gases has also developed to a point where it's now possible to do these measurements on very small amounts of gas concentrations. So I think there is incremental improvement, but for the most part, we still use techniques which were available already 30, 40 years ago. There are some scientific developments on clumped isotopes, very complicated measurements for which very few analytical facilities exist. And my personal experience is that when it comes to deployment of these techniques in an industrial context, it has to be simple, it has to be fast, and it has to be cheap. So anything which takes 4 months to generate results and is very expensive usually gets not deployed in industrial context.
Thank you. I'll turn it to Mary Kang.
Thank you so much for that context, Dr. Mayer. I have, just to pick up on the industrial context, a lot of the methods that you described, of course, companies do use them. How widespread are, the even just stable isotopes and the gas dryness used in the environmental monitoring context and in the well integrity monitoring context? Are they used enough? Are they used sufficiently? I guess that would be this is a kind of an open-ended question.
Yeah, a lot of that depends on the regulator in the jurisdiction, what they require to have done. In Alberta, Western Canada, we had development of coal-bed methane plays between 2004 to 2011. And because these coal-bed methane plays were relatively shallow, a few hundred meters depths, the regulator required that baseline analysis in groundwater were done on every groundwater well within 600 meters of a CBM well, and that included carbon isotope fingerprinting of any methane or higher alkanes which was there. the gas composition analysis, and by default, you get a dryness or wetness parameter, which can be calculated. Industry, I'm less, they don't share all what they're doing, but I'm very confident that they have similar data for their resource plays. And many companies do mud gas profiles, I think, for their own protection. I don't know how frequent and whether they do that once every township or every well, because it does cost some money. But I'm sure most companies have mud gas profiles just to be legally protected if claims are made against which they need to defend themselves. So in my view, it's probably fairly widespread used both in environmental monitoring, if required by the regulator, as well as in industry. However, not all of these data would always be publicly available.
Thank you for that. Noelle, can I ask more questions unless other people want to jump in? I don't want to monopolize the time.
No, of course. Yeah, feel free to go ahead, and if anyone else has questions, just use the raise hand function and we'll work our way around.
Okay, I'll jump in and ask a few more questions. Yeah, thank you for that answer. That's really helpful. I just wanted to ask a bit about shallow groundwater characterization. Both in terms of how do you know if a sample is a good representation of the baseline condition? And then the second question is, how much monitoring is sufficient? You mentioned the 600-meter limit kind of for groundwater monitoring that AER chose to limit for the coal bed methane monitoring at groundwater wells. 600 meters away. Like, is that sufficient? So how much is sufficient? And also, like, how do you know what's baseline?
Yeah, both are loaded questions, and there's not a simple answer to all of them. We have done groundwater monitoring. Let me start differently. So the program I mentioned before on CBM, groundwater baseline monitoring, required one sample to be taken prior to drilling, when drilling could commence, and so on and so forth. So one sample was viewed sufficient because, well, the workload, the onus on whoever needs to do that, and the cost just multiply if you do it more frequently than that. We had a study where we went to the same well repeatedly, and I would have to look up probably 10 to 20 times. And it very much depends on what parameter you're most interested in, how much variability you would find. But intriguingly, for that well we studied, the carbon isotope ratio of the methane in the groundwater remained essentially within measurement uncertainty over repeat sampling over several years. So for that parameter, I would say if you have one baseline number, you're pretty have pretty decent information. Your second question, remind me, was on? I can't hear you.
Sorry. What is sufficient
the
to
radius.
characterize? Yeah, and the radius.
Yeah, the radius which was chosen at the time, looking at it back, I think was relatively arbitrary. If you had leakage of methane around a oil and gas well into the groundwater and all that methane dissolves, I think ideally you would like to know what the groundwater flow direction is, how fast it goes, and then monitor downstream all information which is usually not available at a monitoring site. But it's unlikely that you would have transport for several hundred meters, at least in our environment here in Alberta, where we have fine-grained materials, till, and so groundwater flow directions are groundwater flow velocities are more of in the meters than in the hundreds of meters. My last slide alluded to the fact if your gas leakage were to occur as a free phase, I don't want to say all bets are off, but it becomes very difficult to predict where it goes, in which direction, and how far. So in that context, picking a number out of a hat, what's enough, is equally or even more difficult. So I don't want to be in the regulator's shoe to determine what that radius must be.
That's really helpful. Thank you. Well, I'll just ask one more question while we're on that. Also, in terms of the timeline, we talked about radius and sufficiency in terms of spatial distance. And you said you went to one well over 10, 20 times. Is that over years, months? If you can give us some guidance on that time scale and just your general thoughts on how often we should go back and measure.
Well, the study I mentioned was a baseline study, so we went there over several years and reanalyzed methane contents and carbon isotope ratios of a methane. And that carbon isotope ratio hardly changed because the methane always comes from the same source. Concentrations might be a little bit higher, might be a little bit lower. Very much depends how you sample as well. There are artifacts you can introduce by whether you sample free gas, dissolved gas. So that's a little bit more variable, but the carbon isotope fingerprint just wouldn't move because the methane always came from the same source. Now, if you talk about measurements after, after impact, then in that area we do have very little experience because most of our work has been baseline. The jurisdictions in Alberta are such that in order to do follow-up analysis, it needs to be triggered by the landowner. So the landowner needs to first decide or claim there was impact to the groundwater, and then subsequent sampling would be done. And very little of that has occurred, at least with our involvement.
Great, thank you.
Any questions from the other chapter group members? Let's go Eilish and then David.
Hi, yeah, I heard that, I mean, I'm not a microbiologist, but one of my colleagues is, and she was saying that, naturally you can have these methane seeps, but, microbes in the subsurface can convert them to like CO2. Have you seen any similar kind of, behavior? Because we're, in developing, even in advanced technologies and in monitoring, just, maybe, developing guidance on what we would want to monitor for. And I think that all kind of also plays into the, what's the radius that we look at around.
Right.
Well, and I know it is, it's impacted by groundwater flow, things like that. But I was just curious if you had detected anything like that.
Yeah. Yeah, so we do study methane oxidation, which is a process which does occur in many different fashions. It can be aerobic methane oxidation or anaerobic methane oxidation, coupled with iron reduction, nitrate reduction, sulfate reduction, you name it. Certainly a process you have to be aware of, especially because it changes the isotopic signature of the methane itself. By enriching the heavy isotopes. So if you had microbial methane with very low carbon isotope values, which gets oxidized, it drives its isotopic signature in a direction which appears to be more thermogenic, and that can lead to false assessments if you only look at the gas. But as a groundwater geochemistry research group, we look at all other parameters as well. So not only the methane which gets oxidized, but also the CO2 which gets produced. It would have a very specific carbon isotope fingerprint with carbon-12 enriched if that happens. And we look at the other parameter which are affected. Redox processes always have two half reactions. The methane which gets oxidized, but then also either the oxygen, the nitrate, or the sulfate which gets reduced. And so if you look in the whole context, you should be able to identify whether that process occurs and to what extent it has happened. However, not with one simple analysis, right? When in that case, it becomes a lot more complex. Now, if you had a significant leakage of methane and ethane around a wellbore, for microbes to microbially oxidize all of this in rapid time seems to be challenging, I would say. So these redox reactions need to have a right niche in terms of redox environment. So at a well where a significant leakage occurs, I think the chances of finding the original trace or the original movement of that gas which has not been oxidized yet are relatively high. But yeah, you're correct. One has to be aware of methane oxidation.
Thank you. Any follow-up to that, Eilish?
Do you have any publications that we could potentially reference to? And some of this, I think we'd like, just like to have some papers.
Yeah, I certainly can put a list together and make that available.
That would be excellent. Thank you.
Great, thank you so much. Let's move to David.
Hey, thank you, Dr. Mayer, for the presentation and speaking with us today. It's been very interesting.
Can you check your microphone? I'm not quite sure. I don't hear you very well.
Hey, can you hear me now?
A little bit better.
Okay.
Or if you just speak up, it might be better.
It could be my Cajun accent, so I'm from South Louisiana.
No, I don't think that's the problem.
No.
Okay, go ahead.
All right, I'll try to speak loudly. Anyway, can you clarify, of all the monitoring studies that you've done, is it prior to the well being plugged and abandoned? Is this during its active life cycle or even during its idle? Or is this after it's been plugged to regulations or standards, and after the fact, so post-plug monitoring to understand usage? And if it has, what type of numbers or data do you have in that?
Yeah, so we have never been involved in a study where a well has been plugged and we monitored afterwards. What we are mostly involved is baseline analysis of soils and groundwater prior to drilling a well. In very few cases have we taken samples after drilling the well, and in all of those cases we have not found gas migration from reservoir level if we had sufficient data to judge that. We have also been involved in a few studies where methane has been artificially injected, sometimes methane, ethane, and propane, to see what tools can be deployed to follow the movement of that injected gas, either in soils or into shallow aquifers. And that was very insightful. And I think the only other aspect I should add is that our research group has also been involved in CO2 injection for CO2 sequestration, and where we monitor not only for CO2 but also for leaking methane as an indicator for well integrity. And so that's where our expertise comes from. But I restate, we never looked at a well after replugging it.
Okay, no, that's helpful. Like I said, that's kind of the charge of this whole study for us, is understanding what's that long-term integrity look like. Knowing what we know about when the well is still standing up, we obviously know that surface casing vent flow is a problem really universally. So, I guess a second question, and it may be a loaded question as well, is I think it's great in that you get this baseline data, and that's what we're learning is a little different in the U.S. with these orphan wells. These are wells that the owner is now, walked away from. They may be several decades or even a century old, so we don't have the greatest data, if at all. But we know what we see at the surface or what we may, when we come upon that well. But still, in all, you can still take gas sampling to try to fingerprint if the well is leaking methane today prior to going into the plugging process, and you fingerprint whether it's thermogenic or biogenic. What are your thoughts on risk management as far as at what length do you do to shut that off? If it was a biogenic shallow sand, which may already be, is there, in a perfect world, we don't want to have any gas leakage. Because there's, when you say significant, that's a different, what is significant? How do you, judge that based on what is the ultimate consequence to the environment, consequence to public health and safety and all that? Is there open-mindedness to a risk-based approach? But certainly when you go to try to remediate that, there may be a point of diminishing returns on how what lengths you take to shut that off.
Yeah, that's a whole number of questions. And here in Alberta, we have more than 400,000 wells, which were drilled since the 1950s. Some of them leaking, many don't. In terms of risk management, I think the approach here is, and there are two areas, methane leakage into groundwater and methane leakage into the atmosphere. So from surface casing vents, they're relatively easy to measure what the gas fluxes are. And I think the logical approach would be to try to fix the super leakers, the ones which have the highest methane emissions into the atmosphere. And if you catch maybe the 3% of those, you might be able to reduce 50% of the emissions and not so much worry about the ones which trickle methane into the atmosphere, because there's a cost involved with all of this. And so if you want to achieve something in terms of greenhouse gas reductions, start with the big leaks. On the groundwater side, it's a little bit more tricky, because we often, if the leakage occurs outside of the surface casing vent, the shoe of a well, then it's harder to track where the methane goes in the groundwater. And as I mentioned, if it migrates as a free gas, it becomes even more of a lottery. So where it's I think a factor of doing groundwater analysis to see whether there's clear evidence of methane contamination, and then see what type of users in the vicinity would be impacted by gassy water, which potentially can be explosive. So there's a health risk in that area. But yeah, I hope I got to most of your questions somewhat vaguely.
No, it does. It helps, right? I think it's hard to standardize approach. It depends on if the well is in a remote location versus an urban area. There's a different risk profile to it, and I just want to make sure, or in your personal opinion, like I said, there should be a logical, pragmatic approach to this, because the problem is such a widespread. You have 400,000 wells. There's up to 140,000 wells in the U.S. that the governments, are truly orphaned and are having to deal with. How do we? I'm in agreement. We should go after the heavy hitters first, right? To make the biggest bang for the buck.
Yeah.
Thank you.
Thank you for that. Let's circle back to Mary Kang.
Sorry, I have so many questions, but this I wanted to ask about microbial methane production. We talked a bit about oxidation, but with the mud gas sampling, you should see, would that give you an idea of how deep microbially produced methane can be found? Because as you drill, you're getting the mud, right?
Yeah,
And
yeah,
so
yeah, yeah.
there's always this question of like how deep are the microbial methane sources?
Right. Yeah, and to some extent, in terms of addressing the charge the panel has, I'm not sure how important that question is. And the problem why I'm slow with answering is there's not a clear cutoff in the carbon isotope fingerprints where we say a more negative value is always microbial and a more positive value is always thermogenic. There's a pretty large gray zone in between, I would say, from minus 50 per mil to minus 70 per mil, where the carbon isotope value of methane alone will not tell you whether it's one or the other. If the carbon isotope values are more negative than minus 70, minus 80 per mil, yes, that is indicative of microbial. If they're higher than minus 50, but there's no clear-cut boundary. And so I would say that mud gas measurement alone would not be suitable to tell you where that border is. There's temperature limits, obviously, you could imply, and help with making that assessment. But more importantly, that mud gas profile simply tells you how the isotopic composition changes as you go down. And if you have gas leakage, and you measure an isotopic composition at the surface casing vent, as you know better than I do, in fact, you can estimate where the leak might occur, and that kind of helps you then with deploying your cement squeeze techniques to potentially address the problem. So whether that gas is then microbial or early mature thermogenic is of secondary interest, in my view, in fixing the problem.
Oh, thank you for that. I totally agree with you. Just picking up on that, you showed like the Milkov and Ethiop plots, kind of characterization. I think, I don't know if you showed it for the dryness versus 13C, but you showed another one. Maybe it's not Milkov and Ethiopian, sorry, where you kind of show where the regions are for thermogenic, microbial, and so forth. And my understanding is that all of that is based on, looking at a lot of samples, a lot of known origin samples, and kind of mapping that together. I just know one publication, Milkov and Etio, published something, compiled like something like 20,000 samples globally, and it sounds like a lot, but it's also maybe not a lot. And how much uncertainty or how is in those kind of using those predefined areas, and how could or may how might they change? And so it's kind of a similar question.
Yeah, there's always a risk of using these textbook diagrams which try to summarize the whole planet into one diagram, and especially on what we call the shell diagram, where carbon
Yes.
isotopes versus hydrogen isotopes are shown. There's a significant uncertainty in it because the hydrogen isotope values of the methane and the ethane and propane are dependent on the water in which that hydrogen-containing gas is formed. And that water can be quite different depending whether you're in the Arctic regions, in temperate regions, or whether you're in inland regions such as Colorado or Alberta or Texas for that matter. So yeah, considerable variability. I just looked at the diagram I showed. It uses the Ethiopia and Milkov publication, and they have a fairly clear cutoff between microbial gas versus early mature thermogenic. In my discussion with colleagues, Carles Mühlenbachs, for instance, that's a lot more uncertain where that there's no clear boundary, I would say. So some people claim that early mature thermogenic gas can be generated at very low temperatures and would go much further into the microbial field, whereas others are arguing that microbial gas can have quite high carbon isotope values. And so, yeah, a lot of scientific discussion around that. But again, for the purpose of detecting in which depths the gas leaks, I'm not too worried what we call it, as long as we know whether it's in 300-meter depths or in 600-meter depths, because that's what the drillers need to know.
Yeah, thank you for that. Are there other questions? I don't want to monopolize the time, but thank you so much. I could ask another question if Noelle gives me the okay.
Yeah, I think it's okay. Just a quick time check. We have 13 more minutes left. Yeah, so we'll see where we are closer to the hour. Thanks, Mary.
Yeah, I mean, I could ask a bunch of different questions, but one of the things that I'll just pick up on Alish's question about microbial processes. You mentioned about different geochemical parameters. Do you have some experience working with like microbial community analysis and how to kind of put that together with the geochemical data? If you could just kind of speak to that.
Yeah, we since, I don't know, maybe 5 years, we collaborate with a microbiology team here at the University of Calgary, which does DNA fingerprinting, proteomics, and the whole gamut of new microbiological tools which can be used to identify not only which microbes are in the subsurface, but also whether they're active and what exactly they do. And certainly a steep learning curve for somebody like me, but intriguing information coming out of that, which essentially revealed in contexts like shallow groundwater where methane occurs, is that there are all kinds of microbes around using that methane and producing that methane. And it turns out that both of them are active at the same time is kind of a gist sometimes. But in groundwater, which is highly reducing, where we geochemically argue that all parameters indicate that methanogenesis happens in situ in this aquifer, microorganisms, by one or the other pathways which exist. The microbiologists then confirm that the microbes are there, and they are geared, can do that. But they also find at the same time methane oxidizing microorganisms. And so turns out, I think the microbiology points to a much more active cycling environment than our geochemical parameters would indicate. But it doesn't kind of counteract any conclusions we have made based on the isotopic and chemical parameters about the source of the methane. So it's complementary and intriguing, provides new insights, but again, it has requirements in terms of how the samples are taken, how they're stored, and how quickly they're analyzed, which are not always easy to implement on an industrial site.
Great, thank you for that.
Any other questions, Mary? I think you might be taking us home here.
Oh, I mean, I do have more questions. I have a long list. I mean, while we're on that topic of the complexity of the microbial activity in the groundwater and in the aquifer in the saturated zone, I mean, there's also a lot of activity happening in the unsaturated zone. So that's one question. Another question is, so it's not just methane that we're worried about. We're worried about a whole range of environmental risks. For example, hydrogen sulfide production can also happen in groundwater. And other environmental impacts, other air pollutants, and you could leakage of methane may be creating other dangerous compounds or in groundwater if people were to use it. I don't know if you can speak a little bit to not just methane but other concerns, and then the unsaturated saturated zone, that's a separate question, I guess. Thank you.
Yeah, let's start with the unsaturated zone. If methane leaks up there, yes, oxidation by oxygen reduction is the logical fate of that methane. But if the flux is high, these reactions might not be fast enough to consume all the methane. Ideally, we like it to be converted to CO2 because of the greenhouse impact being less, but large leak versus small leak probably makes a difference. Yes, in the groundwater, so if methane intrudes into an oxic aquifer and it makes the aquifer more reducing, the consequence is a whole sequence of potential reactions, such as iron reduction, manganese coming up as a groundwater contaminant. If you get into bacterial sulfate reduction, yes, H2S becomes a problem. Now, if free iron exists in the aquifer, that will precipitate. So it's extremely site-specific. Arsenic could be mobilized. So all of these, there are all kinds of potential negative impacts. Our studies, which looked at those, indicates they do occur, but often in fairly small environments around the wellbore, and then very site-specific because it depends what's in your sediments. If there's no arsenic, you don't get arsenic reduction. If there's no manganese, you don't get that problem. If you have free iron in groundwater or iron 2, then H2S will not become a free gas phase. So hard to make general statements about that, except to say that all of these processes are an option. In Alberta, we have our shallow groundwater is often quite surprisingly reducing already. So if methane leaks into it, and there's already biogenic methane, some of these geochemicals, should I call it side reactions, do not occur because they already played out in the natural environment, interestingly enough.
Great, thank you for that. You know what? Well, can I ask just one last question? Sorry. So we had this. The monitoring section is broken down into environmental monitoring and well integrity monitoring. And for geochemistry, we had a lot of discussion of whether trying to put that within a subsection for those two, environmental well integrity monitoring, or keeping it separately. I just wanted to get your thoughts on how you would structure that, because there would be a lot of repeated text to
Yeah.
That's why we thought we'd do it separately, but would love to hear
Yeah.
your thoughts on how best to communicate this.
Yeah, and I don't want to tell you how to write the report, but my notion would be to not have it as a separate third
Okay.
chapter. In my view, geochemistry is one tool of several you would use. You would probably do pressure measurements and hydraulic head measurements and all of these. And geochemistry plays in pretty much all the analysis you do in the soils, in the groundwater, in the mud gas profiles in the reservoir, but it's not the only tool, and on its own, it's also not as useful as in combination with others. So my gut feeling would be including all the tools you need into environmental monitoring and all the tools into well monitoring that cuts down on duplication of text, and you also don't give the impression that there's one magic tool out which resolves all questions. You want to use all the tools at your disposal, and geochemistry is just one of them.
Great, thank you for that. That's very helpful.
All right. Okay, any final questions or thoughts for Dr. Mayer? Hearing none, Dr. Mayer, thank you so much. We definitely threw you into this hour at full speed. So thank you. I really appreciate you taking the time, and I'm sure the our committee members here do as well. And it seems like we will likely be in touch with you again over email. Yeah, and aside from potentially asking additional questions, I'll keep you posted on the status of the report and when we intend to make our pre-publication available online to the public. And with that, just thank you so much again, and enjoy the rest of your day and have a great weekend.